Alright, we're going to take a look at how Dijkstra's algorithm can be used to find the shortest path from A to Z. There's lots of ways to get from A to Z, but each edge has a certain weight attached to it, so we have to try to figure out the best way to get there and also prove that no other way would be better. And Dijkstra's algorithm will do just that. The way we start is we start at the original vertex A, we add A to our visited list, right, because we've now considered A, and we explore all the paths we can take of step 1 from A. Every vertex starts off labeled as infinitely far away, but as we visit vertices along the way, we'll be able to update those labels. Dijkstra's algorithm is a greedy algorithm based on the label. So once you're at A, you can reach B at a cost of 3 coming from A, which is better than infinity. We can also reach C at a cost of 2 coming from A, which is better than infinity. A has already been visited, so we're going to look at all the unvisited vertices, B, C, D, E, and Z, and choose the one that has the cheapest cost. That'll be C. So we record that we considered A, then we considered C. We circle C in both the graph and the table over here that's keeping track of our labels. And now we look at where we can get to from C. From C we can get to B at a cost of 1 plus the 2 that it took to get here for a total cost of 3, but B already is labeled as 3, so we're not going to do any better with that. We can get to D at a cost of 5. 5 is certainly better than infinity, so we'll relabel D as 5 coming through A and C. And then we'll also be able to reach E this way at a total cost of 6, which again is better than infinity. So now we're looking at 3 vertices here, well 4 if you include Z, that haven't been visited, and we want to choose the cheapest one available, which will be B. So we'll add B to our list, we'll come up here, and now we'll start exploring paths through B. From B we can reach D at a cost of 7, right? But 5 is better than 7, so we're going to leave it at 5. From B we can also reach E at a cost of 5, and 5 is better than 6, so it turns out that it's cheaper to get to E going through A and B than it is going through A and C. Okay. Sorry, we visited B over here, so we should circle that as well. Okay, so now we're down to 3 unvisited vertices, D, E, and Z, and D and E are tied. Generally, when you're following an algorithm, you have to have a way to make that decision. We usually just go in alphabetical order, so we'll just choose D over E. If you chose E here, it wouldn't be wrong. You just want to be consistent. So we'll stand in D. From D, we can reach E at a cost of 12, but E is a lot cheaper to go directly from B. But we can also reach now Z at a cost of 10. Right? If we go from A to B, actually, sorry about that. A to C to D to Z, because we get to D through C. That's actually a cost of 8. So Z will get labeled as 8 from A to C to D. Okay. I just want to erase that path so that when I see other paths, that's not cluttering my screen. Now I have to consider going through E, which has a cost of 5 because 5 is cheaper than 8. And when I go from E to Z, right, that comes up with a better route and a better cost of 7. So I get to E through A and B. Right? And now the only thing left to do is to visit Z. Right? And once I throw Z into the list, I have my shortest path. So it went from A to B to E to Z at a total cost of 7. Okay? If you update all the labels, and you always choose the cheapest label of the unvisited vertices, Dijkstra's algorithm will guarantee that you get the shortest path. It takes a few times to get used to, but with some practice you can get the hang of it.